All right, good afternoon, and thank you for coming to this special joint RAL ACOM seminar for our very own Dr. Shima Shams from RAL. And just a little background on Shima. She's a talented scientist here at RAL who is working on a variety of topics and has been with us since 2021. Going back through her biography, she earned her PhD in engineering science at the Washington State University, and where she worked on ozone variability. And prior to that, worked on her master's in photogrammetry and engineering at Tusi University of Technology in Tehran, and studied dust storm detection and monitoring, and also got her bachelor's in civil engineering at the University of Tehran. So since joining NCAR as a postdoc researcher in 2021, Dr. Shams has built an interdisciplinary research program spanning remote sensing, air quality and fire smoke monitoring, satellite data assimilation, and land cover change research. And her recent work includes characterizing aerosol retrievals over Africa, advancing air quality forecast tools for Eastern and Southern Africa, and assessing post-wildfire forest recovery using remote sensing. And beyond her research, Dr. Shams is deeply engaged in mentorship and community building here and abroad, elsewhere, from mentoring SOAR's proteges and research fellows at UCAR to co-organizing workshops at NCAR, AMS, and other places. And her contributions have been recognized with the NCAR Advanced Study Program Graduate Fellowship and also a President's Leadership Award at Washington State University, among others. So please join me in welcoming Dr. Shima Shams.
Thank you so much for the great introduction. It almost made me emotional thinking about the whole past and future. And thanks a lot for joining to this seminar among the busyness of the summer for everyone. So today I'm going to talk about the kind of the overarching goals of what we learned through a NASA SERVIR project with the title of kind of toward a resource-aware air quality system with a study case that we had in Eastern and Southern Africa. And I appreciate all of the collaborators that worked through this project. And this is probably not even the exhaustive list. So one outline of what we're going to talk today, a little bit of introduction and motivation of the project. And then we're going to go into three different aspects of the work, which kind of also are reflected in three different papers. And then we're going to end with Beyond the SERVIR and some of my more recent work, and to kind of tie it with the future activity that kind of still like tied back to the air quality. It is known, at least to many of us, how important it is to study air quality, but I borrowed this slide from the State of Global Air, which really still, even for us to know, is very striking. Air quality is the second risk factor for deaths around the world, after high blood pressure, and for children under 5 is the second factor of death after malnutrition. We're talking about 8 million deaths, and this is from this report. I've seen other literature that goes way above this number. So there are a lot of different respiratory and chronic diseases that comes with air quality. It's extremely important to be able to have the forecasting system, to be able to have warnings, and eventually really try to mitigate the negative impact of air quality. So here is the study area that the NASA SERVIR project was focused on, and this plot is just the average of 10 years from CAM's reanalysis data. It's a global data set, so of course a lot of the regional and local sources are not represented. But still we see that majority part of the domain is not under compliance for the interim target 1 and 2, and of course the 3 and 4, which are the goal, basically puts the whole region under the not meeting the target. And in this region, we have different sources for air pollution, basically, from anthropogenic emissions, biomass burning, and dust burden. There's also a lot of the household and cooking pollution. We're not covering those. This is kind of ambient air pollution, but acknowledging that's also a very important factor. Aside from that, what we are seeing right now with the population these days, where the reality is the population growth is expected for Africa, with potentially most of the largest populated city in the next 50 to 100 years will be in that region, which really create more complex situation for the air quality. So NASA SERVIR project was framed around co-production and co-development of the air quality forecast system through data assimilation. And so just the importance of data assimilation in any air quality, the emissions have a lot of uncertainties. The boundary condition also put a lot of different uncertainty there. So with satellite data really help us to be able to navigate some of those limitations. And here I just showed 1 day of VIIRS data. Pretty much every day that I look at, there's some interesting thing happening. We're just seeing some biomass burning, and how it shows in VIIRS, and some as dust activity. So it's really critical to use the satellite data such as VIIRS to inform our design. And the project was intended to have a strong engagement, and it was started as a co-development on the proposal stage. Then project was funded. We work with a local regional agency named Regional Center for Mapping in Resources and Development in East Africa, and planned 2 weeks of visit where you can see the logo of agency that we've been in touch with to make sure that revisit the proposal mandate and proposal goals and make sure it's in line with their goals. During the meeting, also Meteo Rwanda was identified as the main agency to take over the initial operational system. So throughout the project, we had a lot of testing to make sure that the transition of the system would happen. Unfortunately, this goal was not realized for 2 main reasons. First, our main person of contact in Meteo Rwanda got another job in outside organization, and that's something that you need to always, keep in account. And so we were thinking our head, okay, how we can navigate through this, maybe identifying another agency. And then the biggest hit happened, and we had a big cut by NASA and some limitations of not being able to do at all the transitioning. However, we really tried our best to at least articulate what we learn and have the system in a way that eventually put us in a good situation to have the actual training and transitioning. So this is the schematic of the overall different components of this project. I'm going to start this presentation with something that is really tying to my background. Data assimilation was new to me, but observation covariance error is something that I've even done in the FTIR retrieval. And just recognizing that we do not have uncertainty estimate of VIIRS over Africa made me think that we first need to figure it out and be able to use it into our DA system. Then we're going to talk about the overall, what we learned, the potentials and the limitations of DA over this region with the data set that we have. And we will end with the lesson learned in general of how we can have resource air quality system. So with this paper, I had the pleasure of working with Rob Levy, who is one of the PI of Dark Target, to make sure how I'm characterizing the error is consistent with their understanding. And so like any other data sets, it's always important to understand the uncertainty of the data that help us to really make sure that the limitation and the capabilities are reflected in how we are interpreting the results. And whenever we're talking about data assimilation, that even puts the uncertainty estimate as another important factor, because that's how you, in a data assimilation, it just shows like how you want to nudge your results, how much uncertainty exists in model, how much exists in the observation. That balances out like how your data assimilation would perform. And another part that we wanted to look at in terms of uncertainty assessment was to look at it from the perspective of, do we see any impact and influence from the aerosol size distribution? And with the size distribution, I'm going to just shortly say that fine particles with the 0.6 micrometer, those are usually coming from smoke in biomass burning and anthropogenic, often have like a more regular shape, versus the smoke, versus the coarse mode with the larger diameters, they also have usually less regular shapes. So for this study, we were looking at VIIRS, which is the one that we are using is on the NASA SNPP launch. There are NOAA, 2 other launches with NOAA, which we're not targeting for this study. Some details of data is mentioned here, but the most important thing is there are 2 different algorithms that the retrieval is using based on the surface characterization, dark target and deep blue. So we're going to look at both of these to identify which one has less uncertainty to be prioritized if both of them exist, as well as in the data assimilation, my goal was to have a specific observation error for each. And AERONET is basically the ground truth for the aerosol optical depths characterization. Itself is a sun photometer, and it really gives valuable information on aerosol optical and microphysical characters. And we use the level 2 observation to just make sure that it is the highest caliber of the data. And here you're seeing the 35 stations that we used over the 2020 to 24. So we have an updated estimation of the error over Africa. So for part of it, for understanding the size distribution, there is not a really clear indices from the remote sensing side, but angstrom exponent is a good tangible index. It is not directly, is not a linear relationship between that and size distribution, but overall, if it is close to 0, that shows a coarse mode. If it is close to 2, that talks about fine mode. But around 1, that's where you have the mixed phase. And there are a lot of studies that they look at different clustering, incorporating different aerosol property to come up with an index. Here in this work, we wanted to just focus on distribution-based analysis rather than coming up with a cluster method. And to make sure that the data set is robust enough, for the part that we are looking at, AE, everything is AOD plus, AOD larger than 0.2. So it's kind of like starting to have a moderate load of aerosol at least. So I'm sharing this plot, which was very interesting to me that we had such a strong signal. This is aggregation of all the AERONET data over the whole region. And all together, they're showing a very strong monthly variability. And in particular, let's pay attention to the April. That's the time that we can see median is much below 0.5, and the whole box fixture is toward that domain, which shows that the April we have so much dust activity and not really that much of the smoke or the fine mode. On the other side of this, we have August and September, that both medians are above 1.5 and the whole boxes kind of in that domain. In those months are fine mode aerosols. We had the expectation that these are mostly smoke related. We did not anticipate the anthropogenic emission being higher, and that was confirmed looking at other literature. So we found in a study looking at the Bairn area, which confirmed that these 2 months have a lot of Barren area, and another study which was much older, but look at MOPIT and saw the CO signal also peaking around this month. And we also look at the spatial variability, and with clustering of a histogram shape for each station, which nicely showed that the Dust Bowl in North Africa is picking up, and we see those stations being blue, and Southern Africa, Southern Central Africa, mostly with fine mode. So now getting into the fun part of pairing, which is like the main goal that we started this process because we wanted to validate and understand the uncertainties of VIIRS. So I'm not going over all the detail, but we took the kind of the standards of what is needed to create these both sampling from the VIIRS and AERONET to make sure you have a robust data set from each coming into your pairing. So the validation showed that both algorithms are doing a great correlation with the AERONET data. And here we also looked at the distribution of data. It was not normal, so we used non-parametric Spearsman correlation rather than R-squared that we often look at. And a couple of interesting points, even in the correlation map, was the drift that we see at the higher AOD. And so both of the algorithms are showing that on high AOD, there is an underestimation from VIIRS. And that's something very important to kind of reflect from early on. We will come back to this, but that basically means if we have extreme event, potentially VIIRS is showing a lower AOD. So those are the times that we care the most and we want to capture, and there is a chance of not getting that extreme value that is happening. And then we also did the binning to estimate the error envelope, which is shown here by EE. Basically, you bin the data, and based on the mean and a standard deviation of each, you need to regress the lines and come up with the domain that at least 67% of your data is fitting. And that EE basically will become the observation covariance error into the data assimilation. We also looked at the monthly variability, doing some to make sure about the number of data sets is robust enough. We did some Monte Carlo sampling as well. I just want to go over a few things. So April, which we already know, it's mostly dominated by coarse mode, showed the worst kind of uncertainty estimate that we had, which kind of ties back to this that we talked with Rob a lot, that in both of the algorithm, particularly in a dark target, there is only one aerosol mode, one aerosol model that they are using for coarse mode. And so that's only capture very certain type of aerosol characterization for dust activities, versus some recent study are showing that even a dust particle could be carbon coated and have some absorbing properties. So that kind of shows that there is room for the next generation of retrieval algorithm to really expand on the number of aerosol models that they are using. And another interesting part was seeing that August and September, which we know are dominated by fine mode, showed us the best performance. So deep blue is showing really operating very well when it is dealing with smoke particles. So the conclusion of this part, yes, it was a very strong monthly variability of AE was observed, and which just showed that we do have significant cycle between the coarse mode and the fine mode. Both algorithms showed a good agreement versus, however, deep blue was performing slightly better. So whenever in the data assimilation we have both of them available, we give priority to deep blue. And then we also look at the uncertainty estimated for the region, and it also showed that for the smoke, potentially it will perform better. And so now let's dive into the DA part. This is the chart of the details of the system that we have for the region is WRF-Chem, a go-card for the chemistry and aerosol, and GSI, which is a 3D VAR data assimilation framework. What I have here as highlighted with blue, that's the part that we just talked about, that we characterize the uncertainty of AOD products, and that will go into the DA system. And you can see the rest of the emission and boundary condition details that we're gonna pass over, but happy to talk if anyone has a question. And for these parts, we focused on the case study of June 2022. The 22 part is just random, but June was selected because I look at different maps, and at least it has it has both dust and biomass burning activity, and this is just average over CAMs, 10 years of CAMs is showing that a lot of activity is expected for the region, and it is outside the bimodal rainy season, which is a slightly different from which part of the domain we are looking at, but at least it's outside it. So as I mentioned, we are not going to talk in details about the equation that we needs to minimize in DA, but paying attention to the two matrices, B is the observation covariance error, and B is the background, which is basically a model covariance error, and R is the observation covariance error. So as I said, that's the part that your quantification of these two help the system to know which way it should lean and with what degree. So for the background, for the model background, we use the double factoring of emission, and the GenBE is a common tool in WRF-Chem, which help us to estimate the horizontal and vertical lengths. And for the R, we already looked at that paper that what we went through to estimate the covariance error, and we have it separated for each product. So I implemented this part that the DA will use different uncertainty based on which product it's using for the pixel. So here, looking at the months of June 2022 average for what we see in the background, what we see in the data assimilation, and what the subtraction of those talk about. I think this histogram kind of shows us to kind of reflect on what we see here in the map as well. The black line is VIIRS, and the red one is model. So on a smaller load of AOD, the peak density in VIIRS was higher than the model. And the assimilation is picking up on that. And that's probably why we have these kind of smaller increase in the data assimilation in average that we see. And the other part of talking is the highest number. So VIIRS is not seeing anything above 1, which in one side we already talked. VIIRS also has this issue of whenever we're talking about heavy aerosol load, it might not really catch up to that. But for this part, we need to trust what it is saying. And the data assimilation is reducing the density of those high values. But we wanted to better understand, is that the right direction, how it is doing? So we need independent observation, which kind of ties to the most challenging part of this study. So I'm going to talk about each figure separately. What we are seeing here for each algorithm is if there was no cloud and all data were clean, we would have had dark red color over the whole domain. But what we are seeing is that, and this is like over the whole months that I'm looking at. So there are areas that we did have such a little amount of observation because of the cloud that exists in the area. So that's one aspect of it. And so for instance, for the black one, the black dots here are AirNow stations. And unfortunately, all of them, we did not have a lot of data around those points. So we would not expect the DA system to do a lot when there is no satellite observation to do things around those. For the AERONET stations, which are showing in blue, at least 2 of them were doing interesting stuff. So we're going to look at those. But another challenge here is all of these stations are not really located on the enhancement part where we have the heavy load of aerosol, like as here. So we really did not have a lot of observation on those sides to talk about what's happening over the most enhancement, what direction is good with the ground-based observation. So just diving into these to kind of help to see what the DA is doing and when it has data, when it doesn't. So black line being the AERONET data, and the star here is where we had VIIRS on the 60-kilometer grid around that point. There are times that we don't have even in these. So you can see like here, we start to have like a large difference between what the model versus observation does. And the DA is helping reducing probably the impacts of more surrounding points like outside the 60-kilometer, but we really do not have observation around that time. So the satellite is, and that's coming to this part that is sometimes it's cloud, and there is also this challenge disentangling between cloud and retrievals. When we are talking about a very heavy aerosol load, it could still be tagged out as cloud. So sometimes there's also that challenge. And so, for the other station, you know, all of them were kind of close and it was doing fine. But I didn't want to let it go without having more understanding of, okay, what is happening in the enhancement part. So I also look at MODIS, so it would be 21 hours into forecast is not necessarily the best time of looking at DA impact. It already has a lot of model recycled into it, but still helps to see what we are learning. So here is MODIS for the hour of its overpass. And then we created the same data sets, cleaning whatever MODIS is missing, and then aggregating for the whole month. And it is showing something that that the background versus MODIS is showing enhancement, like it has overestimation, large overestimation compared to MODIS. And if we put this next to what the data assimilation was doing, it was reducing over this area. So in overall, at least it makes sense how it is working, and the MODIS next to that observation is helping to have that confirmed. But again, like acknowledgement of the cloud missing data still also are strong in MODIS as well. So in general, for conclusion of this part, the potential of DA is really shown and we see it. And the uncertainty estimate was really a nice practice of having the DA system tuned around the characterization of error for the region. We see that the bias is reduced, but it does not have a homogeneous impact around the region. And we are dealing with this like cloudy condition. It's a tropical regions on top of a sparse reference observation. But there are some feature stuff that makes it even more interesting, and that's looking at geostationary satellite, particularly that it could help to see some open windows between these clouds. And that's the discussion that we have with Kathy. And now European satellites such as MTG, they have this infrared sounder, so you can potentially incorporate the CO into the DA, and also it has the AOD. So there is a great potential to be able to see if that could help even have a stronger system. So going to the third part of this. So we have this dilemma or challenge that the science community wants to capture the complexity of our system. And that naturally will end to more complex modeling. which have more parameterization, a bigger setup, versus on the other side, on the operational side, that could very well translate into a steeper learning curve. And we are talking about too many inputs, too many configuration that would be imposed to people who are already few on a staff and have heavy workload, and on top of limitation in the computational capacity. So there is a balance here to make sure whatever complexity we're adding, we also keep account of the usability of it and how that can be translated in our design. Going back to this slide, I want to say we were through the co-development and the discussion that we had with the stakeholder in the region, knowing that they often are working with one standalone system, some of this decision of using go-kart as our scheme, we are aware that there are more advanced schemes, or GSI is a 3D VAR system. But we wanted to make sure that it can be run on a standalone system. And you need to start small to make sure it can be run. The other part is data assimilation was something new to me as well. So it really helped me as someone getting introduced to it to see how complex this input structure of the DA is. And there are distributed among so many different directories, and you need to set up inputs in so many different places. So to make it easier for myself to have a workflow, and with an eye that eventually we want to have it transition to people and have it really two things: it's transparent and they can see some intermediate visualization, as well as it kind of also does that on-demand training, because you can add a lot of input so you can read about it and then visually see what components are happening, rather than running a bash code that you wouldn't be seeing what's exactly happening inside. So this is kind of just one examples of how it can also help, like having a documentation of all of the details. And this is where you just put all of your input somewhere, and it will automatically go and fit it in where it should be located. And also visualization of intermediate results. I believe I'm a very visual person. I like to see my maps and make sure that they are meaningful and they make sense. And I think for users, for any operator, eventually it will help them to know what they're doing. For instance, for this day, if you're in Rwanda, there's really not that much observation in Rwanda. So you would not expect things happening. And here we're showing that what product we are using. As we talked about, we are giving priority for deep blue, but the dark target has a more relaxed way of dealing with cloud, so it helps a better coverage. So the user can also develop this sense of understanding of what is happening in the region, rather than just looking at the final output. This is also another example of where we use the Python notebook to create some tools to download CAM data and create some time series and maps based on the discussion that we had. They need a lot of these to be incorporated in their annual reports, so that helps to minimize the workload and have everything streamlined and having a standard. And this is another example of the dissemination. If it is, we tested the system, that the NASA geospatial app that they have, and it could potentially be very helpful if they want to have their own warning system. And that helps to have this characterization of like, what are the people, who are the people are coming and checking on them. And it's relatively easy to use compared to if you want to develop something from scratch. And of course, always it's helpful to make sure that the visualization are targeted to whoever the final audience are. So the conclusion for this part is just accounting that when we add the complexity, it could potentially add some increase in the onboarding and operational development. So at least being mindful of that and making sure that we are also reflecting on the usability and the documentation. and making sure the workflow is accessible. And we showcase the Jupyter Notebook as a tool to really help with the numerical model being more usable, and hopefully the end goal would be a really nice user interface rather than like the terminal work that we are used to. So now a little bit more of what I'm doing these days and kind of tying back to what we learned here. So I got interested to also look at low-cost sensor because we, in many parts of the world, we do not have enough observation. And but dealing with those, you need to have an understanding of their error. And if we have a good understanding of the error and we have a large network distributed in interesting region, it really helps us to even use them into data assimilation. So here with one of my source students and colleagues in UCP who are developing the low-cost sensor, but recently added the air quality, we tried to come up with the workflow to create the cleaning of the data and then doing some calibration as TRIA station. We had it paired with EPA stations. And then another interesting part of like now that I'm touching modeling was looking at the high resolution modeling. I did some exploration of large AD simulation, and one of my source students was looking at 2 different setup of runs that we had to see the impacts of the different hair forecasts versus the analysis. But the example that I'm showing just quickly here is we were working with the forest the prescribed burn people on the Forest Service, and they mentioned that the example of the fire that you're showing here on April 9th got impacted the Atlanta airport visibility. And it was quite a big deal if a prescribed burn reached that. So it was a test case, but the large AD simulation worked well. So the inner domain was in 100 meter, and this is the time that we see a couple of hours after the fire. The simulation is really showing how it is impacting the visibility over Atlanta. I'm also working with David on looking at the characterization of biomass burning smoke on NO2 using another geostationary satellite, which is located on kind of Southeast Asia. And so aside from the details of the model comparison, what we are putting together as a framework of everything being comparable in a satellite data and modeling, we are developing it in a way that it can be merged to Melody's Monet, which is a software between NOAA and NCAR to have a really standardized framework to validate model and satellites and all other observations. Some upcoming work. This project is accepted. We will probably start it in October. Finally got a time to look at tempo, and my role would be a lot of a statistical analysis to oversample and see if we can see the enhancement of local refineries, oil gas refineries from tempo data, and hopefully with the final goal of if we can be helpful in reporting any leaks or any enhancement in the emissions. Another very interesting work is kind of like tying more back to my PhD and like upper atmospheric work that I was focusing on. But this one has a very interesting machine learning question that I'm excited to deep dive. It's a couple of different sensors, which each one have different vertical and a spatial and kind of temporal sensitivity and the fingerprints. And we have this fun problem of putting them all together to create a harmonized data, which can be useful for many applications for the carbonyl sulfide. And another part that it's really close to how I see my career trajectory evolving is I do see the impact of air quality, whether we are looking at anthropogenic emission or fire or the dust. it has a lot of societal impacts, but it's also very complex air system that we are looking at. And if we are looking for a true solution that really talks to the usability, we need to work into interdisciplinary convergent science work. So we have more than just one discipline tracking the solution, and potentially it could have a high reward of better sustainability. And within that, we just finished the summer colloquium just last Friday. We had the end of it, which was amazing, and that was toward compounding events, which is extremely important also in regard to air quality and fire. We have other events really tying to this. Whenever we have drought, we create the condition for the fuel. Whenever we have fire, it really talks to a lot of flood activity. So, and then like the whole urban design and how that corresponds to air pollution. So it's very interconnected system. And I look forward for some of these proposals that we have to come true and be able to have a deeper dive into this. So with that, I'd be happy to have questions.
All right, thank you for that wonderful talk and the impressive overview of your research. I will take both questions. We'll take questions here and also online. So for those online, please do enter your question in Slido. So first in the room.
And the room has the
Yes.
microphone, so like you don't need to.
Sorry, I'm a co-author of the paper and should have asked it during the paper stage. But why are the deep blue uncertainties are higher, I think, during June, July compared to the dark target? Otherwise, the dark target was always higher.
It is, I think like, let me see how much higher we're talking about.
Yeah. So look at June and July. So the dark target has only 0.06 of AOD.
Yeah.
But dark deep blue goes to 0.24 and 0.17.
So I will go back to what we see here. So June, July, especially July is kind of interesting in terms of what type of aerosol it is showing to us. We thought that Rob has this idea that probably July we have more of mixed aerosol. It is not like mix of fine mode versus coarse mode. It is like mixed aerosol we are seeing. And there is a chance that a deep blue might not capture those waves. Those are pretty complex. Like that's none of the retrieval are really have any sophisticated model dealing with mixed aerosols. They usually account for like what percentage could be from this and that and kind of coming up. But mixed aerosol could potentially be a domain that creates the higher uncertainty for both of those. And seeing the differences, there is also a little bit of like the sampling. So we tried with both of them for this month are doing similar numbers. So that should not be the same issue. But yeah, as I said, like some could be just that mixed aerosol issue.
But in your DA, you are saying when deep blue is available, use it, otherwise use the dark target.
Yes, and yeah, because we are not doing the month by month selection. Like potentially we could, and then I'm saying based on which months we are looking at, we could select differently.
Anyone else? Yes.
I want to find out what influenced your choice on studying Eastern and Southern Africa?
Eastern and Southern Africa.
Why did you focus your studies on?
So I think it goes back to like, you know, who are the collaborators that you were in touch with. I feel like for this proposal, we needed to make a decision based on who have been working on, and Rajesh can add more to it.
I can say it. So the SERVIR program, it has regional hubs. It had regional hubs. The program doesn't exist anymore. And so one of the hubs is in the Eastern and Southern Africa. There was also a Western Africa hub that came about in 2024, but that proposal poll never happened. So they had 5 hubs, one in South America, one in Hindu Kush Himalayas, which is basically Nepal, another in Southeast Asia, one in Eastern and Southern Africa. And so the call for proposal asked to focus on a particular hub, And that's why we focused on Eastern and Southern Africa to start.
Okay.
Yeah. If there was another call, then West Africa had
Yeah.
the hub at that time, but unfortunately that
And
was
we
canceled.
submitted LOI for Western
but
Africa.
we didn't do it.
Unfortunately, the changes in administration priorities canceled that call.
And also I want to find out, the topic for the presentation was centered on Africa, but I realized heading towards the last part of your presentation, you drifted to low-cost sensors, focusing on Atlanta and other parts of the US. Why?
Oh, the end of. So that's my current project. That's like, unfortunately, right now we do not have a lot of outside and international works going on. So we are doing our best to capture what we had and be ready for next opportunities to come, and happy to have like the collaborations going on. But at the moment, I don't know like how you're familiar with how NCAR operates. We are mostly self-funded. We need to be active with whatever potentials are there, and all of these kind of contribute to each other. So if we have a good lead on how to best use the low-cost sensors, or how to have the larger assimilation handling a situation in any part of the world, then you are also able to look at it. So the beyond the SERVIR part, it is not really talking to necessarily like, low-cost sensor, of course, it always can be, it is toward the kind of resource that we're looking at. But we also need to make sure we have funding to survive, to be able to correspond to future calls.
Okay, other questions?
Sorry.
Go ahead.
And lastly, I want to find out, to wrap up, what will be the overall enhancements this work added to air quality focus over the Eastern and Southern Africa?
Yeah, we showed over the large enhancement that we are seeing in the dust and both dust and the biomass burning. The initial model without the data assimilation had way much more kind of overestimation, so we reduced those.
Thank you.
Sure.
Any other questions? Yes.
Yeah. You showed how the VIIRS underestimated the AOD when it was high, and I was wondering how systemic that is, and if that can be in some way. It seems like a limitation on your DA process. So is there a way that can be factored out in some way? And is it widespread for VIIRS, or is it just something you saw?
Yeah, that's a very good and hard question. Like how systematic it is. We see it in previous also literature that VIIRS is susceptible to that. How the retrieval teams can handle it, and it's usually, it would be not a good handle if we do it on the project base by base and saying like we're gonna. However, especially we cannot do it in a region that we have such a sparse data. If it was like, probably in a more dense network of AERONET, it could be a way of kind of the bias correction after the DA. I've seen like some of the discussion of JEDI that they try to mitigate the final bias after it. But in terms of the retrieval, it is more of acknowledgement. I think both teams are kind of aware of it, and maybe like in future of how they deal with the aerosol model, they can think about. But it's not an easy problem to resolve.
Thank you.
So what you mentioned, the sparsity of the data is one of the problems here, especially with the cloud over Africa. And looking, from VIIRS and stuff. What are the opportunities? You mentioned the IRS and the potential of having geostationary observation. Are there some other VIIRS available as well, aren't there? That you could potentially, some of the other VIIRS missions?
Oh, some of the other VIIRS mission, like NOAA.
That a possibility? Or, just to finish off as well,
Yeah.
what are the options for, it seems like you have a framework here where you could actually, with a kind of an Aussie type setup, come up with some ideas of where you could potentially locate some aeronets and some additional AERONETs which could, especially in some of the areas where there's high uncertainty or potential for huge impact of understanding air quality for populations. Can you come up with some ideas of like more AERONETs or ground stations?
You asked a couple questions, so let me make sure I'm answering them one by one. So on using NOAA data, there is a potential there, but it's also needs a bit of change in the system because it does not have the true algorithm that NASA has. So you need to have completely a different setup of how you are taking the input into the DA system. Then we also need to think about, like, we were just talking with Rajesh for another proposal in Saudi Arabia that maybe we use the geostationary ones and incorporate more data. It would be same thing. We also need to think about, like, are we staying in 3D VAR, or do we want to have multiple nudges viewing different times? Using AERONET data, I think that would be very interesting if we can have them deploy. The reality of the region is like DRC and Sudan are unfortunately has some geopolitical issues. So it won't be that easy to say we're going to develop a couple of AERONET in the area and be able to use them. So it's that could potentially be more challenge versus the other part of the domain. There is a potentials there. I think with the cost of AERONET, if we can have more of mid to low cost sensors and have them in larger number, and that's easier setup, like we can work with the schools, we can work with universities to have the setup and potentially not that heavy amount of calibration and maintenance that the other sensors require and the training that you need. So these low-cost sensors that the UCP team is building is basically 3D printed. That's really an easy setup to just have it in the region and then being able to print those and have them, of course the sensors you need to purchase, but it's very cheap, like, with $100, $200, you can have the whole package. And we're working on some extended version of these sensors to have more gas species to be included in those. And if we have like a dense network and then we characterize a few and then harmonize the rest of them with what we have, I think that, I'm not sure, but I feel like that's probably an achievable goal in a few of the countries that we can have this set up and it's easier to navigate through those.
Very nice work, Shima. So, do you consider the secondary aerosol generation? Secondary aerosol generation in WRF-Chem? Because secondary
Aerosol, yes.
Yeah, because I noticed that your domain, there's quite a few big cities, and maybe also transportation.
Yes.
So I guess there's gas phase, chemistry that create a secondary aerosol. Some of the bias in the aerosol simulation, I'm not sure if it's related, but it might be related to the.
That's a great point. With the go-kart and wanting the system being easy and computationally light, we are not accounting a lot for the secondary. Also, it is one of the ongoing large uncertainty that we have in these whole simulations. So that potentially could lean into it. Another factor is these, like the emission inventory, the anthropogenic emission inventory that we are using in CAMS is a global. We are not using anything local and we couldn't find anything local. So before even getting there, a lot of the local sources that could potentially, like in the paper, we are discussing that potentially some of the smaller scale that what Air now is seeing, we won't be able to resolve it with this like high resolution, like Gridpoint of CAM. So, and with that not being there, we don't want to like overburden the system when we know we are not really having that input. But that's again a very good question and pointing to this, like having some ways of creating localized emission inventory would be a huge gain, especially when you want to get really into the details of city air pollutions.
Thanks. Okay, we're running at the end of the hour, so we'll wrap up, but I want to invite you to speak with Shima after this, or she's always around, so hopefully
Thank you
this will
so much,
spark
Chris.
new discussions and collaborations. Thank you again for this wonderful
thank you.
presentation.
Yeah, thank you so much for all the great discussion, and happy to talk more about it.